Hi, I'm Lauren Mendelson, and today we're going to talk about chirality and its applications in organic chemistry. So what exactly is chirality? To say that something is chiral means that it cannot be superimposed upon its mirror image. In other words, it does not have a plane of symmetry. Look down at your hands. To the untrained eye, they may appear to be exactly the same. However, if you attempt to place one on top of the other in the exact same orientation, you will realize that it's impossible. Your hands are actually non-superimposable mirror images of one another, meaning that they are chiral. This is why the word chiral comes from the Greek word for hand. This term was coined by Lord Kelvin himself. Chirality has a lot of direct applications in organic chemistry. Because carbon can form 4 separate bonds in a tetrahedral fashion with bond angles of 109.5 or less, a carbon atom can form a chiral center. Notice in these 3D drawings that these two molecules are both 1,1 chlorobromopropane, but that they are actually two different molecules. They are non-superimposable mirror images of one another, or stereoisomers. For a molecule to be considered chiral, it must contain at least one tetrahedral atom with 4 unique substituents bonded to it, and it can have 0 planes of symmetry. We call one half of a pair of molecules that are non-superimposable over one another an enantiomer. As a pair, they are enantiomers. Chirality is important when we talk about selectivity, which is the measure of the enantiomeric purity of a solution. For a solution to be enantiomerically pure, it must contain only one enantiomer. If a solution contains more of one enantiomer than the other, it will be an enantiomeric excess, which is expressed by a ratio of the quantities of each enantiomer. A racemic mixture is a special case in which a solution contains a 50-50 ratio of enantiomers. One cool property of chiral molecules is that they are optically active, meaning that they can characteristically rotate plane polarized light, which is light that travels in only one direction. A pair of enantiomers will rotate plane polarized light the exact same number of degrees, but in opposite directions. A racemate will not rotate plane polarized light at all. To speak about the two different enantiomers of a pair, we label them as R and S based on the order of their substituents in space. This does not tell you the direction in which they will rotate plane polarized light. This may all seem abstract, but it has some very real and serious applications. One famous example is the drug thalidomide, which is a pregnancy medication that led to thousands of birth defects. This happened because the effects of only one enantiomer of the compound were studied, but both were given. Chirality does not affect physical properties such as mass, but it can affect chemical ones. Therefore, chemists strive to create reaction conditions which will result in high E or enantiomeric purity. A chiral molecule can create another chiral molecule or a racemic mixture, but an achiral molecule can only create a racemic mixture. Therefore, it is important to pay attention to chirality in every step of a reaction. In my organometallics research lab at Dartmouth, I am attempting to synthesize the chiral NHC catalyst shown here. Chiral catalysts can be used both to speed up reactions and to promote selectivity. We hope that the research we are doing today can aid the development of new pharmaceuticals tomorrow.